All right, here we are going to look at how to compute the lateral surface area of a solid of revolution. So if I take a function and revolve the area under the curve about an axis, how do I find that lateral surface area? So when we found volume of surfaces of revolution, we approximated our pieces as basically cylinders, right? Straight-sided cylinders. And that was good enough. Okay, we were adding up infinitesimally many of them, right? They were super thin with delta x, right? But when we're finding surface area, we want as good of an approximation of that actual surface that we're going to see as possible. And so rather than approximating these things as cylinders, we're going to approximate them as what they most closely resemble, and that is truncated cones. And in order to compute the lateral surface area of a truncated cone, well, it's very similar to the area of a cylinder. So remember, lateral surface area of a cylinder would be the circumference times the height, so 2 pi r times the height. So it's very similar for the truncated cone, but instead of the height, we're going to use this slant height. And because we don't just have a single radius, you use the average radius. So it's 2 pi times the average radius times the slant height. And for us, our average radius if you're dealing with a function that's being revolved about the x-axis, that average radius is just going to be the function value in this case. Now, certainly if you're revolving about another axis, you'll have to make some adjustments, but for our purposes here, that's just going to be the function itself. So adapting this to the model of adding all of these things up, we can say that our surface area for a solid of revolution, so lateral surface area of a solid of revolution, then is going to be 2 pi times the integral from a to b, right, so whatever that closed interval is, times your radius, which again for us here is just going to be the function value itself, but this is a more general case, and times that slant height. Now, remember from our arc length video that we can get that hypotenuse of that triangle by taking the square root of 1 plus the derivative of the function squared. And so that's what we're going to do to find our surface area. So let's take a look at a fairly simple example. So our example that we're going to look at is the function y equals 2 times the square root of x, revolved about the x-axis on the closed interval 4 to 9. So fairly simple function here. So let's do a little sketch just so we can get an idea of what we're looking at. So there's our 2 square root of x function. And if that's 4, and that's 9, well, if I take the square root of 4, I get 2, so that puts me at 4 here. Square root of 9 is 3, so that puts us at 6 here. Again, just to get an idea of what's going on with this function. And so we're revolving about the x-axis, and then we're going to have this surface. Actually, that's not a straight line, is it, right? That's supposed to be my, yeah, there we go. There's my square root function, right? And so we're just looking at what is this lateral surface area here. Yeah. Okay, so my formula says that my area is going to be 2 pi times the integral from, in this case, 4 to 9. My average radius is just going to be my function value. So here, 2 times the square root of x, and then times the square root of 1 plus my derivative squared. Well, so let's take a look at our derivative. Maybe we didn't compute that earlier. So if y is equal to 2x to the 1/2, y prime is x to the negative 1/2, or 1 over the square root of x. So we're looking at 1 over square root of x squared dx. Cool. So we're only dealing with positive values of x. So this whole thing is going to work out pretty nicely, I think. So if I go ahead and pull this 2 out, I'm going to write this as 4 pi times the integral from 4 to 9 of the square root of x times the square root of 1 plus 1 over x. Cool. So this thing is looking really, really nice. What I'm going to do next is I'm going to get a common denominator under my radical. And that's going to give me x plus 1 over x. And when I split up that radical, what I'm going to have here is square root of x over 1 times square root of x plus 1 over square root of x. So my radical x's are going to cancel, and this thing's working out super, super nice. So we have 4 pi times the integral from 4 to 9 of the square root of x plus 1 dx. So super, super simple integral to compute. If I just do a u substitution, x plus 1, my du is dx. If I do an indefinite integral of u to the 1/2 du, I'm looking at 2/3 u to the 3/2 plus a constant. But whenever I substitute this thing back, I'm looking at 4 pi times 2/3 square root of x plus 1 cubed evaluated from 4 to 9. So we're looking at 8 pi over 3 times, let's see, what do I have here? Square root of 9 plus 1 cubed minus square root of 4 plus 1 cubed. You know, not super pretty numbers by any means, actually pretty similar numbers to the ones that we had in our arc length example. So we're looking at square root of 10 cubed minus square root of 5 cubed. That's just 10 root 10 minus 5 root 5. I mean, I could kind of leave it like this if I wanted to, but I'm going to write this maybe as 80 pi root 10 over 3 minus 40 pi root 5 over 3. Yeah, we'll leave it like that. So that's surface area.